Hi guys, this video is made to help out students solving gas law problems, and the four that I'm going to be addressing in this video are Boyles' law, Charles' law, the combined gas law, and the ideal gas law. And those are four that I teach in my chemistry class, and they're four of the more commonly studied ones. All the gas law equations are basically describing how different properties of a gas change under different circumstances. And we're going to kind of hit each one in turn, and I'll give an example or two how to solve a math problem involving each equation. If you're looking for a specific one, you can skip ahead in the video to when I talk about that, and I'll put the time codes in the description. So let's dive right in here, and we'll start with Boyles' law, which is probably the easiest of the gas laws. Certainly mathematically, I think it's the easiest to do. So let's just take a look at it first, and then I'll do a math problem to kind of illustrate how this works. So Boyles' law is read as P1 V1 equals P2 V2, and it's describing how does the volume of a gas change if you start messing with the pressure, meaning like if the pressure increases, how does the volume respond, or if the pressure decreases, how does the volume respond? And that's what these symbols stand for here. So I just wrote out a typical problem that you might see involving Boyles' law. So let's read through it first. It says if a gas has an initial volume of 2.5 liters under 0.75 atm of pressure, atmospheres of pressure, what is the new volume if the pressure is reduced to 0.25 atmospheres? So one of the things I try to emphasize in my class with gas laws is that the math isn't super hard, like the algebra isn't crazy hard. But what can kind of trip people up is that when you do these problems, a lot of units are thrown at you. In this one, we're dealing with pressure and volume. Other gas law problems might throw in temperature there, or even moles. So you get a lot of different units. And one of the things you want to be careful of is that your units are consistent. Meaning, if, say, the volume on the left side is liters, then it has to be liters on the right side too. So sometimes the problem might have, say, liters and milliliters, and you'd have to convert it so that they're the same. So keeping track of your information is really important when you're doing gas law problems. And that's why I recommend, especially when you're first learning these, that a good way to kind of keep yourself organized is just kind of write down the information as you're going before you even do the math. All right, so let's say I'm trying to solve this problem. One good thing to do, I think, is just on the right-hand side to kind of write down the information you already have before you even think about the math. Let's just organize our thoughts here. So let's go through this again one more time. We have a gas with an initial volume of 2.5 liters. So what's that? Well, it's 2.5 liters. It's our initial measurement, so that's got to be our initial volume, our V1. So I'm just going to write 2.5 liters. And it's under 0.75 atm of pressure, so that's our P1. So let's write that down. All right, keep going here. What's the new volume if the pressure is reduced to 0.25? So 0.25 has got to be my P2. And V2 is the thing I'm solving for, so that's my unknown. Okay, so in all these problems, you'll have one unknown. The problem should give you all the other variables, and then there'll be one that you need to solve for. Okay, so we got all our stuff organized now, and now you can take those numbers and plug them into the equation here. So let's do that. So we'll look at this equation, and we know that the P1 is now 0.75. The V1 is 2.5. And the P2 is 0.25. And V2 is what we're solving for. Okay, so we have our math problem here. And now we just have to solve it algebraically. And I always tell my students there's a lot of ways that you can solve these. So pick whichever one works best for you as long as you arrive at the correct answer. But the way I always describe it is, remember in algebra problems, what you're trying to do is isolate the variable. Meaning we want to get this V2 all by itself. We want to get rid of any other number that's with the variable. So the way that we do that in this problem is we want to divide by 0.25, because if we do that, that cancels that right out, and now V2 is now left by itself. on the right-hand side. So we've isolated the variable. And if we did something to the right side, then we have to do it to the left side as well, right? That's a big rule in algebra. So we divided by 0.25 here, so we're also going to divide by 0.25 here. And what that's going to leave us with is 7.5 for our answer. And what you should do at the end there is then think to yourself, okay, wait a minute, this is chemistry class, so I need some units in here. I'm talking about a volume, and I want my units to be consistent with what I started with. So if I started a volume of liters, then my answer should be in liters too. And there we go. So we kind of got our answer just like so. Okay. The good thing about these problems is you can always go back and check to see if you got it right by taking that answer that you just got there and plugging it back into your equation and checking, is 7.5 times 0.25 the same as this? Okay, and that's one way you can check yourself mathematically. A way you can kind of check conceptually is just ask yourself, does my answer make sense? And by that I mean, we'll go back to the original problem here and think, what actually happened to this? Well, the pressure went from 0.75 to 0.25, so the pressure went down. So if you're not squeezing something as hard, if you're kind of letting off the pressure, then it makes sense that the volume would increase. And it did. The volume went from 2.5 to 7.5. So that makes sense, right? We went from kind of a higher pressure to a lower pressure. So things should get bigger. The volume should get bigger. And that's another way you can kind of check. It's not 100%. It's not always going to tell you if you got the number exactly right. But we would know that it was wrong for sure if my volume was less than 2.5. Like if I solved this and I got 0.5 as my volume, that doesn't make sense, right? Because the pressure went down, so the volume should go up. Okay. All right, so that's Boyles' law. Let's try Charles. Okay, here's Charles' law. And Charles' law is still dealing with volume, just like Boyles, except now we're talking about temperature. So we don't care about pressure now. We just care about temperature. How does the volume of a gas respond if temperature is involved? And I'm going to try to do two problems here for you guys because Charles' law is a little trickier algebraically. I found that some people have a little more trouble solving these ones. So I'll do two for you guys with Charles' law. I would start these the same way, and by that I mean writing down the information that you have. So let's do that. All right, V1, T1, V2, T2. Let's go through the problem. Gas has a gas at 270 K, and remember K stands for Kelvin, which is the unit of temperature that we're going to be using here, because kelvins don't have negative numbers, so that the calculations work. All right, so we got 270 K. That's got to be our T1. Okay, and a volume of 0.55 liters. And the question says, what's the new volume? Okay, so we're looking for V2. That's our unknown. If the temp is increased to 330 K. All right, so there's our information, just keeping ourselves organized here. And before I even solve the problem here, I can kind of predict like what should happen. Well, what's happening? The temperature is increasing. And when you heat things, the molecules start moving more and they start kind of spreading out a little bit. So before I even do the math, I can predict that my volume should get bigger. My V2 should be bigger than 0.55 because the temperature went up. Hotter things move more and they get bigger. They expand, right? Think hot air expands because the molecules are moving more. Okay, so let's set up the math problem here. So our equation is V1, so I'm going to take my V1 here, 0.55, divided by my T1, 270, equals V2 is what I'm solving for, and T2 is down here. Now notice, guys, I'm not putting units in the math problem here, and I know that seems weird because usually you do that, like in stoichiometry, for example, you have to put in your units. I recommend you don't do it when you're solving the math, just it can get very confusing when you already have variables and then you're also putting units in there. So if you put them on the side here, I think that's good, and then just at the end remember to put in your unit once you solve for whatever V2 is. But when you're just doing the straight math, forget the units for now. It just gets confusing if you put them in. All right, so what we're trying to do is get V2 by itself, isolate the variable. And the easy way to do that is to take this entire term and multiply it by 330. That is going to cancel out like so. And what that'll do is give us our V2 isolated on the right-hand side there. And algebra, once again, if I did it to the right, I have to do it to the left. So I'm going to take this entire term and multiply that by 330. Okay, so then you use your calculator, of course, and you would do 330 times 0.55 divided by 270. And if you do that, you get 0.67 as your answer. Okay, and lastly, once again, because we're doing volume, we want a unit of liters because we started with liters. So 0.67 liters. That's our answer right there. Okay, so there's one Charles's Law problem. Let's try one more. Paper here. Okay. All right, so same problem, slightly different, and you'll see that when I start setting the things up here. So V1, T1, V2, T2. Okay, going through it. This time we've got 270 K. We've got a volume of 0.55 liters. And this time the problem is giving me the volume. So I have my V2 as 0.45 liters, and I'm looking for the temperature. Okay, so it's really similar to the last problem, except this time we're solving for T2 instead of V2. And I found in teaching this that that's a problem that people have more trouble with. Trying to solve that algebraically is a little bit trickier. So let's set it up and I'll show you what I mean. Okay, so here's our V1. Here's our T1. Here's our V2, and here's our T2. All right, so what we're trying to do here is solve for a variable in the denominator, which is, like I said, a little trickier. And once again, there's different ways you can solve this. I know some people like to kind of do this cross multiplication thingy. What I like to do is get the variable out of the denominator. So it might seem a little weird, but what you can do is kind of multiply both sides by T2. Kind of bringing the T2 over to here. And what that does for me is it gets rid of my fraction. It cancels that out here. So on the right side, all I have is 0.45 now. Okay. And you can simplify this in the middle if you want to. You don't necessarily have to. If you do that, you go 0.55 divided by 270, and it's going to come out to be a pretty small decimal. So what you would get is T2 times 0.0020. Okay, so that number is just this simplified 0.55 divided by 270. And once you get to this step, that's a lot easier, all right? Because we're almost done now. So to isolate the T2 completely now, we would just divide each side by 0.0020. Okay, that cancels out, and we get T2 equals whatever that is, which comes out to 220. And since we're dealing with temperature, our units are Kelvin. So there's our answer. Okay, so that's a little trickier, right? Because you've got to get that variable out of the denominator, bringing it over to the left side. And that's one way I think that works pretty well when you're doing these. All right, so that's Charles's Law. Let's try probably the hardest one, the one that people have the most trouble with. And that is the combined gas law. Okay, so combined gas law is probably the hardest because now you've got 6 variables. This is when both pressure and temperature have to be considered. So there's 6 different things here. So a lot of information that goes on in these types of problems. But solve them the same way, right? Keep yourself organized. So write down P1, V1, T1, P2, V2, T2. Okay, let's go through the problem and try to figure out what's what. Okay, gas has a volume of 18 liters, so here's our V1, 18.0 liters. Has a temp of 220 K, there's our T1. And a pressure of 1 atmosphere. Okay, if the pressure is decreased, so now we're going to move to the right side of the equation. The pressure is decreased to 0.41 atmospheres. And the volume is increased to 34 liters. What's the new temp? Okay, so we're looking for T2, which is this guy on the bottom here. All right, so I've been teaching that you take all this information and you plug it into this equation here. And I think that's, in my experience, what students prefer to do. You can, however, if you're algebraically minded, kind of rearrange the equation before you plug some stuff in, meaning you could rearrange this so you get T2 isolated first. In this type of problem, you'd have to bring P2 and V2 over to this side. It's a little funky because you're working with variables there, but that's another way that you can do it is rearrange the equation so that T2 is all by itself and all the other variables are on the left side, and then you plug in all the numbers. So do that if you want. I'm just teaching plugging stuff in and then solving it algebraically. So here we go. P1 is 1.00. V1 is 18. T1 is 220. P2 is 0.41. V2 is 34.0. And we're solving for T2. All right, so this is kind of like the last one that I did where we have the variable in the denominator, and I am going to start by kind of bringing that over to the left side. So I'll take this entire term here, and sorry, I'm running out of space, but multiplying it by T2, so that cancels that out right there. And then we would also take this entire side here and multiply that by T2. So you can do some simplification in the middle of this problem. So you can go 1 times 18 divided by 220, and what that's going to get you is 0.082. And you can do the same thing over here, right? So we can go 0.41 times 34, and that gets you just 14 over here. All right, now this can be a little tricky with the rounding. So if your answer doesn't come out exactly the same as what I'm doing, it might be because of how you rounded this. But you should be close. Okay, so we're going to then just divide by 0.082 and end up with a final answer of 170 Kelvin. And there's our final answer right there. Okay, so it's a little tricky. You just kind of got to rearrange the math a little bit. All right, one to go. There's our combined gas law. Our last one is actually easier mathematically. Okay. So the ideal gas law, it's got pressure, it's got volume, it's got temperature, and then you notice you got this N and this R. And the N stands for moles. So here we're actually dealing with how many moles are in there. And R, it's called the gas constant, but basically it's just a number that you're going to use in all of these equations. And this one's very particular with the units. In order for R to be this number, 0.0821, pressure has to be in atmospheres, volume has to be liters, and temp's got to be in Kelvin. So all these problems I'm doing, there's no units that you have to convert, but once again, just be careful and make sure that you don't have to convert units if you're doing an ideal gas law problem and it gives you milliliters, you have to change it to liters before this will work. Or if you're doing it and it gives you, say, grams of a gas, then you would have to convert those grams to moles before you can plug it into the ideal gas law. All right, let's do this last problem here. So we've got pressure, volume, N, which stands for moles, R, which is the gas constant, and T, which is the temp. Okay, let's look at the problem. Gas has a volume of 100 liters, so there's our V, 100. The pressure is 2. And the temp is 200. And the question says, how many moles of the gas are there? So we're looking for N. Now, it didn't give you R, but remember, R is always going to be that number. It's a constant, so it's constantly that number. So we always can just plug in 0.0821. Okay. All right, and now we just plug it into the equation and solve. So we've got pressure times the volume equals N, which is what we're looking for, times 0.0821, that's your R, and then T, which is 200. Okay, so we're solving for N. We can simplify if we want to a little bit here. So 2 times 100 is 200. Keep N here. 0.0821 times 200, if we want to simplify, comes out to 16.4. And then it's as simple as getting that N by itself, isolating that variable, right? Canceling that out. 200 divided by 16. And what we end up with here is N all by itself. And over here we've got 12.2. And what are our units? We'll go back. What's N? N is moles. So we'll just squeak in the moles right there. And there we go. Okay, so there's the 4 gas law problems. There's others, but those are the only 4 that we're going to do today. And I hope that was helpful for you guys.